Everyone. Welcome back to Chegg's live Gen Chem session. I'm Corinne of Chem with Corinne. I am a chemistry teacher. I loved chemistry so much. I have a couple degrees in chemistry, and I just love teaching chemistry in a way that makes it understandable because it does not have to be as hard as some of your professors want it to be. And Chegg is here to help you. So Chegg feels the same way and wants to help as many students as possible, which is why they are hosting 11 of these free office hours every week. So in terms of chemistry, we have Gen Chem tonight, Orgo tomorrow night, stoichiometry on Wednesday, and then another Gen Chem session on Thursday. So we'll hope you'll join us for these weekly sessions. So we are live for 1 hour, just answering your questions. Put all of your questions in the chat. I will get to them. If I don't get to them tonight, I will start with them next week. And that's where we're actually going to get started today. We're going to start with a question from last week, which was just, can you do a titration math problem where you solve for the concentration of the titrate? And I think so many students right now are struggling through acid-base chemistry. If that is you, let us know in the chat. Like this feed if you are struggling with acid-base chemistry, because if you are struggling with it, I am a teacher, right? Chemistry teachers, this is the one topic that we're all like, I don't want to teach. I don't want to do acid-base chemistry because it is so tricky. So let's talk through some of the tips so you can navigate this tricky topic. So let's just start with titration. So let's start with the basics of titrations. And you probably were exposed to titrations in Chem 1. But we quickly change things up when we're no longer looking at just strong acid and strong base titrations. So let's go ahead. This is a question from last week. How do I calculate the concentration of the concentration of a titrant? So it's important to know the difference. Okay, what's the titrant versus the analyte versus titrate? All of these words can get so confusing so quickly in chemistry. So if you're talking about the titrant is going to be the known solution. That can be the acid or the base. And by that, I mean the concentration that is known. So you're going to typically put that in your burette, which is that long, skinny piece of glassware. And then the goal is to find the concentration of an unknown analyte, which is typically put underneath with some kind of acid-base indicator in it. So you can find the endpoint, hopefully close to the actual equivalence point where your moles of acid and base are equal. You can also have what's known as a back titration. That's a little bit different. If you need help with back titrations, I'm happy to discuss that too. But let's just go ahead and jump into the math because this is what you asked for last week. All right, so let's see. And I forgot to start my live on Instagram. So I apologize if you are just joining from Instagram. That is my bad. All right, let's go ahead and get started with this question from last week. So what volume of 6 molar hydrofluoric acid is needed to titrate 45 milliliters of 3 molar potassium hydroxide? So with a titration problem, the first thing you want to do is go ahead and write out your neutralization reaction, because how you actually calculate your concentration is going to be based on the stoichiometric ratio between your acid and your base. In this case, it's going to be a 1-to-1, but I'm going to go ahead and write out the equation anyway because it's good practice for when things get more tricky. All right, so I have hydrofluoric acid. So I want you to think as I'm writing this out, is HF a strong or a weak acid? So try to answer that in the chat. All right, so I have my acid plus my base. My acid is going to donate a proton to the base, forming water. And then whatever is left over. So my second product is just going to be KF in this case. All right, with acid-base chemistry, you are just looking for the movement of that proton, that H+ ion. The acid is always going to donate one. The base is going to accept it. The acid becomes the conjugate base. The base becomes the conjugate acid. Just some basics with acid-base chemistry. All right, so looking at this, again, it's a 1-to-1 ratio. So I'm going to be able to use that really easy equation. The molarity of my acid times the volume of my acid is going to be equal to the molarity of my base times the volume of my base. How is that possible? The moles are equal, right? So in this, if I'm trying to reach the equivalence point where the moles of acid and base are equal, it's a 1-to-1 ratio. I can just put those two equations together because the moles are not changing. So all I have to do now, my goal is to find the concentration of my acid. I'm just going to rearrange this. I like to do the algebra first and then plug in all of my numbers. If you want to plug in all of your numbers first, you will get the same answer. I think you're just less likely to make a calculator error with this, so that's why I do it this way. All right, so now the hardest part, right, is just making sure you don't mix up any of those concentrations and volumes. So making sure that you keep the volume of the base and the concentration of the base together. So we have 3 molar times our volume. Oh, good question normally comes up here. So do I have to convert it into liters? If I am taking the milliliters and then dividing by the milliliters of something else, if I were to just divide both of those by 1,000, right, it just kind of doesn't matter, right? It's just going to cancel out. So when you're doing a dilution type problem or a problem like this, you don't actually have to convert into liters. So I can just take 45 mils, divide that by my 6 molar. Oh, you know what? See, you got to be careful. You got to make sure you are keeping track of what the problem is actually asking for, right? This problem is asking for the volume of the acid. So the volume of the acid, it's not really going to make a big difference here. It's going to be equal to the concentration because that's what we're given. So sometimes with these problems, it is so easy to make a simple mistake just by misreading the problem. So make sure you're annotating your problem, underline what you're given, circle what you need to find out. All right, so that gives me a volume of 22.5. Again, molarity cancels out. That's going to be 22.5 milliliters is my answer. Let's double check for sig figs. My initial concentration only has 2. So therefore, my final answer will need to have 2 sig figs to match that. So that would be 23 milliliters of hydrofluoric acid. If you were here for the beginning, I said, okay, is hydrofluoric acid a strong or a weak acid? It is a weak acid. So what you need to know is even though hydrofluoric acid is a very destructive, very caustic acid, it is not classified as a strong acid because it doesn't fully dissociate in solution. So know that definition. A strong acid is one which completely ionizes or separates out into its ions in solution. There are 7, you just need to memorize them. So this is a weak acid versus potassium hydroxide is a strong base. You will need that when you're doing more complicated problems. All right, so that was pretty straightforward, right? If you have a 1-to-1 ratio, the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base because the moles are equal. What happens if you don't have a 1-to-1 ratio, though? So in the second example of just calculating the concentration of an unknown solution, so we have calcium hydroxide is added to hydrochloric acid. All right, again, another neutralization reaction. This is my acid. The hydrogen is going to combine with the hydroxide to form water. And then whatever's left over. So we'll have CaCl2 as our second product. Now we got to balance this. All right, I have 2 chlorine ions. I'm going to go ahead and put a coefficient of 2 in front of HCl. That gives me 2 hydrogen atoms plus another 2 here. Means I'm going to need a coefficient of 2 in front of water. All right, now it's a 2-to-1 ratio between our acid and our base, right? So you have to be careful. So now what I need to do is I need to calculate the moles of my acid and then figure out the concentration of the base. So it's not that tricky, right? Just one extra step. You can't just assume that you can use that same equation. All right, so my chemistry teacher, he was a legend. Long before I took chem, so as a freshman, I remember walking through the halls and there was this teacher running through the hallways screaming, "Hey you, MV equals moles, remember that." I still remember it, right? Obviously, I've done a lot of chemistry since then, but it's stuck in my brain, all right? This is just the concentration, right? This is just this equation, but rearranged. If you can remember it in this order, though, you will use this equation all the time. So the molarity times the volume will give you the moles. When you are doing the volume, in this case, it has to be in liters. So be careful with that. If you get a crazy big number for moles, you've done something wrong, right? Make sure to convert milliliters into liters. All right, let's go ahead and just calculate that. So I have 0.150 molar hydrochloric acid, and I have 30 mils of that. I'm converting that into liters just by dividing by 1,000. And then I just got to multiply that. So let's see, 0.15 times 0.03, 0.0045 molar. Sorry, moles. I was trying to solve for my moles here. So that is the number of moles of acid. At the equivalence point, what happens? Why do we care about the equivalence point? It's that spot where the moles of acid and the moles of base are equal, which is really powerful when doing calculations like this, right? So what I need to know now is that's going to be equal to my moles of base at the equivalence point. If we're looking at points before or after or at the half equivalence point, things are going to be a little bit different. But directly at that equivalence point, our moles of acid are equal to the moles of base. So now I can go back in. I know my volume. So molarity equals the moles per liter. I want to try to solve for my volume. So I'm going to rearrange this a little bit. My volume is going to be equal to the moles divided by that concentration. So I'm going to take 0.0045. Technically, I should have more sig figs, but they just be zero. So don't hate me for that. I'm just going to write it out. Divided by my concentration, which we're not trying to find that. See, I keep doing this. I got to keep track of the problem. Got to keep track of what the problem is asking for. Our goal is to find the concentration. Concentration is going to be the moles per liter, right? So it's already written the way we need it to be. So we have 0.0045 moles divided by my volume, again, in liters. And that will give me my concentration. So 0.2610 molar. Again, double check all of our numbers. We have 4 sig figs in that initial number, 4 here, but only 3 in this concentration. Therefore, my final answer also has to have 3. So this becomes 0.261 molar calcium hydroxide. All right, so just a little bit with titrations just to get us started. This was just a question that was asked last week. It looks like you all are in the chat. Let me hop on and see kind of what you're saying. Yeah, so it looks like on TikTok there are 7 strong acids. So it looks like hydrochloric acid, hydroiodic, hydrobromic, sulfuric, chlorous, nitric, and then you have perchloric acid. You also need to include chloric acid, which is HClO3. So good job with that. So know those 7 strong acids because when you're doing all of the other types of problems and calculations associated with acid-base chemistry, you need to quickly be able to determine whether you're dealing with a strong or weak acid. And again, the definition of strong versus weak is not how dangerous, it's not how low the pH is, it's how much it dissociates or ionizes in solution. Does it separate out fully, 100%? If so, it is a strong acid. If it only partially ionizes, it's still classified as a weak acid, no matter how dangerous it is. All right. So thank you all. So how do I make, okay, on YouTube, how do I make my titration topic strong? How do you get like good at titrations and things like that? You just have to keep practicing. The more you expose yourself to all of the different types of problems, the easier this is going to get. And I suggest like with titration, especially when you start getting into weak acid, strong base or weak base, strong acid titrations, practice, like do some practice just where you are trying to map out a titration curve and you are purposely going through the process at the initial to find the initial pH, to find the pH before the half equivalence point, at the half equivalence point, after that, like purposely make yourself graph it out so you learn how that all of those calculations change throughout that titration. All right. Yeah, and you know what? Why don't we just roll into what's important in a titration curve? So let's look at some titration curves and we'll talk about that. And I think that's one of those things like you take Chem 1 and titrations are so much fun. You're having a lot of fun like waiting for that color change to happen, hoping you don't overshoot the titration, laughing when your friend across the lab does overshoot the titration. And then you get into Gen Chem and Chem 2 and you're like, oh, wait, this is not as fun as I thought, right? So you're no longer just doing strong acid. So let's say we had hydrochloric acid plus potassium hydroxide. All right. So this is my pH. This is going to be my volume of titrant added. All right, so let's just go ahead and like talk through this and then we'll switch gears and do the one that's actually tricky, right? And please let me know what you all need help with. If you are not struggling through acid-base chemistry right now, let me know in the chat and I will jump into that topic next. The goal with these sessions is just to hit on as many topics you need. The more you put in the chat, the better the session's going to be for everyone. All right. And unfortunately, I just got something on TikTok. Yeah, I won't be doing Punnett squares because that's bio. And right now, Chegg does not have a bio feed. But keep asking questions. And yeah, tonight is Gen Chem, tomorrow's Orgo. So unfortunately, there's no bio session yet. But Punnett squares are tricky. I do remember those. I remember that struggle. All right, so hydrochloric acid plus potassium hydroxide. Why do you have to know the strong acids? Because you have to be able to say, oh, this is a strong acid and strong base titration. What does that mean? My equivalence point is going to happen at 7. And what happens at the equivalence point again? The moles of acid are equal to the moles of base. With a strong acid, strong base titration, that's always going to happen at a pH of 7, which is really convenient. And yes, someone just asked, will there be an organic chemistry session? Yes, tomorrow night. So come back tomorrow if you're in Orgo right now. All right, so looking at this, so what am I going to have here? So I'm going to have a low pH initially, right? Because I'm looking at acid. We're going to go up. We're going to have our equivalence point, and then we're going to end with a higher pH because we have that strong base. That's what the strong acid, strong base titration curve looks like. That is definitely like a lot more straightforward than something where you have a weak acid or a weak base plus a strong acid. Let's do a weak acid plus a strong base. So the difference here, right, we're still going to label things in the same way. Volume. The difference is we're going to have an additional peak here. So with, I didn't draw that the best, did I? So with a weak acid or a weak base plus a strong, plus the opposite strong situation, basically we are going to still have our equivalence point. In this case, it's going to be closer to whatever the strong part of that titration is. So for example, this one is a strong base. Our pH at the equivalence point is going to be slightly basic. So it's going to be slightly above 7. So we can just kind of draw that there. We'll end up somewhere up here. What we'll also have is a portion, what we call the buffer zone. All right, so if this is my equivalence point, let's say this is at 40, we'll also have the half equivalence point. And at that half equivalence point, what is really important to remember is that the pH is equal to the pKa. And when you are asked to solve for either the pH or the pKa, this just remembering that fact will help you out so much. All right, so let's see. Okay, so looks like some more questions on. Yeah, so what is a titrant, right? So a titrant is what you are adding to in the titration. So the titrant is whatever it has a known concentration. It's your known solution. Typically, it's put in the burette. It said your lab, you're using silver nitrate. Yeah, so silver nitrate, you might be doing a back titration. So a back titration is called an indirect titration, where you're going to add a whole bunch of excess acid to something that's not normally like easily dissolved. So with my students, I used to do a back titration with eggshells. So eggshells have calcium carbonate. We'd add a whole bunch of hydrochloric acid to those eggshells to get that calcium carbonate to dissolve. And then we'd then titrate whatever HCl was left over. We'd work backwards to then figure out how much we had initially. Yeah, so titrant is going to be the known solution that you're typically adding to the unknown, and that can be either the acid or the base. Okay, let's see. Let me hop back in. Struggling with equilibrium. All right, let's talk some equilibrium then. Equilibrium is another tricky topic. I'd say in Gen Chem 2, or if you're taking AP Chem, the two trickiest topics are definitely going to be equilibrium, and acid-base chemistry is so tricky because you have a lot of equilibrium associated with it, right? You're doing lots of ice tables and things like that, especially with those weak acid, strong base titrations, any of those where you're asked to find the pH, you're also doing equilibrium tables, you're doing the ice tables, you're doing all of that. So it's just so hard. All right, so let's see. Yeah, and then what is the significance of pH being equal to pKa? So if you are asked to find the pH at the half equivalence point, and let's say you have the Ka value, you can quickly find the pKa, and that just saves you a lot of time because if you remember pH equals pKa at that point, you don't have to go through all of those calculations. All right, it looks like TikTok is on tonight. So thank you all for being here. I'm going to just keep reading through this chat and just trying to work through this. So it looks like someone said, I'm struggling with equilibrium, specifically finding the equilibrium constants. Let's talk through like an equilibrium. Um, yeah, let me see. I have a lot of acid base stuff prepped, but let's talk like through equilibrium with that. So let's say I'm going to write out a problem and we'll talk through all of that. So if the pKa of acetic acid is 4.76. I don't know, 0.2 molar solution. All right, so the reason acid-base chemistry, like you get a lot of exposure to equilibrium in this unit as well. All right, so let's go ahead and look at that. So the first thing we want to do, we know the pKa is 4.76. We want to find the pH of a 0.2 molar solution. So where do we start, right? So first thing you always want to do is write out that dissociation equation, because if you're going to be writing out equilibrium expressions or the Ka, the acid dissociation constant, you need to have the actual reaction, right? You need to know what's going on. So acetic acid, that's just going to be H plus acetate, C2H3O2. All right, and then we're writing out the dissociation equation. So we want to show what's going to happen in solution. So when we add this to water, I probably should have put my state there. I apologize. All right, so when we do this, what's going to happen? That H is going to pop off, forming H3O plus, and then whatever's left over, right? So we take away that H, we'll have C2H3O2, the acetate ion. We've subtracted one H. H has a charge of +1. That means my charge is now -1. So that's my dissociation equation. So now if I wanted to write out my Ka expression, my acid dissociation constant, right? It's going to be equal to the concentration of my products divided by the concentration of my reactants. Notice I'm not including water in this. Why am I not including water? Because it's a pure liquid. So pure liquids and pure solids are not going to affect these equilibrium expressions or acid-base dissociation constants because they don't impact equilibrium. All right, so you're only focusing on anything that is aqueous or gaseous. And in this case, I'm looking at the concentration. Remember, with equilibrium expressions, you can also look at the pressures. Sometimes you can also do the moles. Yeah, so it just kind of depends on what you're looking for. All right, so I have my Ka expression, and I want to determine the pH. Where do I go from there? All right, so I know my pKa is equal to 4.76. All right, what does that tell me, right? pKa versus Ka. If you have learned in Chem 1, right, pH is equal to the negative log of H plus. pKa is very similar. The pKa is going to be equal to the negative log of the Ka. All right, so in this case, we don't know Ka, so I'm going to rearrange this log equation. So Ka is going to be equal to 10 to the negative pKa. This is one of those equations that I have everyone memorize because in chemistry, you don't need to be worrying about deriving the log equation, right? If you can do something to save some time is money in this class because you are doing so many other complicated calculations and things. You don't need to worry about the math. Sorry, Wall STEM, don't hate on me for saying that. But just remember how to move this around. So what I'm going to do now is I'm going to say, oh, okay, I could solve for my Ka That's going to be equal to 10 to the negative pKa, which was given as 4.76. So let's see what that's equal to. That is equal to 1.7. How many sig figs? Okay, we'll say 1.74 times 10 to the negative fifth. With equilibrium expressions and with Ka values, you do not need to include units. It's like the one time in chemistry, so enjoy it, because all the other times you need those units, but not for this. All right, so now I have my Ka, and I want to find the pH. What am I going to do now? So I'm going to go back to my equilibrium expression. I can now set that equal to 1.74 times 10 to the negative fifth. All right, let's do some equilibrium, right? If I were to set up an ice table, I would start out, my initial value here would be 0.20 moles. It is a 1-to-1 ratio, so I would subtract x and add x to this and that. We're going to assume that x is so small that it's not really going to impact everything. So what I'm going to do is I'm going to set this equal to x squared over the concentration of acetic acid, which is going to be 0.20 molar. So now all I have to do is solve for x. That's going to give me my H plus value. I'm going to kind of scoot that down here. So x would be equal to 0.00186 molar. Again, x is going to be equal to that H3O plus, which we can also write as H plus. And now I know my pH is a negative log of H plus. So I just plug that in. So my pH in this case would be 2.7295. Let's go back for sig figs with pH. Be careful. This is your magnitude. It does not count towards sig figs. This is where we count our sig figs. So let's go back to this problem. We only have 2 here. So our final answer should also only have 2. So this becomes 2.73 is our pH. All right, so a little bit with pKa, a little bit with equilibrium and acid-base chemistry. So that's kind of just a start. All right, let me hop back in the chat. I know you guys are asking some great questions. Since the Ka is really small, does the reaction shift left? That's a really great question. So that's coming in on TikTok. So Ka is going to tell us, right, the direction of that reaction. So yes, if Ka is small, right, are we having less dissociation, basically, is what we're saying, versus if we had a large Ka value, right, that means we are closer to being a strong acid. So with Ka, really, we're determining like the percent ionization is what it's telling us. And like, the bigger the Ka, the stronger the acid, and it's because it's based on these concentrations, right? So if I have a larger value, that means that I have more of these products, versus if I have a smaller value, it's because I have more of the acid that hasn't dissociated yet. All right, these are all really good questions. Keep asking these questions. This is why I love to do this. This is why I'm here. We are here weekly, and Chegg is here to help you 11 times a week. So even if you're only taking Gen Chem, know that there's another Gen Chem session on Thursday nights. There's also a stoichiometry session, which is Gen Chem content, on Wednesdays. So Chegg is here to help you. Please spread the word. We want to have more students joining our feed, because the more interactive this is, the better the feed is for everyone. All right, so let's see. Okay, I'm just going to start going through all of the questions, and we'll just go through them in order. So starting with, there's a question on YouTube. Oh, sorry, there's a question on TikTok. Can I do a Lewis dot structure? Yeah, so it looks like we're going to do Lewis dot structures, and then we're going to talk ionization energies. And I'll just go in order of your comments. So keep putting in those comments. Worst case scenario, if I don't get to it tonight, I will be answering it for you next week. All right, Lewis dot structures. So with Lewis, there is a process to follow. Let me pull up, let me just get, I don't know. We'll do carbon tetrachloride, just as an example. All right, how do I draw a Lewis structure? There are just a couple steps you need to follow, and you can do literally any structure with a little bit of practice. You got to think of it as you're solving a puzzle. All right, first step, count the total number of valence electrons in your molecular or covalent compound. So in this case, So I'll write out the steps over here. So 1, count total valence. All right, so carbon has 4. Each atom of chlorine has 7. It's just based on its location on the periodic table. So as you move left to right across the periodic table, you're adding valence electrons until you get to noble gases where you have 8. So I have 4 atoms of chlorine in this compound. So I'm going to say 4 times 7 is 28, plus 4 gives me 32 valence electrons. So you're going to count that total, and then you're going to wait until the last step to double check everything. So now you're going to draw a skeleton structure, which is basically where you kind of guess how these atoms are going to come together. There are some cheat codes with this. So carbon has 4 valence electrons. That means it wants to form 4 bonds. Carbon is typically going to be your central atom because it wants those 4 bonds. Nitrogen has 5 valence. It needs 3 bonds. Oxygen needs 2. Hydrogen can only have a single bond. Same with your halogen. So chlorine is a halogen. It has 7 valence electrons. It can only have a single bond, so that's not going to be your central atom. So we're going to go ahead and draw carbon. We're going to connect 4 atoms of chlorine. And then we're going to move on to the next step. So now we're going to make sure we're going to add electrons to satisfy octet rule. All right, and you're like, Corinne, that sounds really fancy. What is the octet rule? If you think of a stop sign, right? It's an octagon. It has 8 sides. So the octet rule is just this idea that most atoms, there are of course exceptions, want to have 8 valence electrons. So looking at chlorine right now, each of these lines represents 2. There are 2 shared electrons in that bond. So we need to add in 6 around each of these. So I'm just taking my time, making a little, doing some art here, drawing in all of those valence electrons. So now my last step, I'm going to double count the total. So double check total, adding double and triple bonds as necessary. All right, so looking at this now, I have 8, 16, 24, 32. This checks out. So I have correctly drawn my Lewis structure. So that's the reason why we find the total valence first, because it's a good way to double check to make sure you're not missing any double or triple bonds. So now I can take this, I can say, oh, okay, so carbon tetrachloride is going to have it's going to have tetrahedral geometry because I have 4 bonded atoms to that central carbon atom. All right, if I had additional lone pairs on that carbon atom, then I'd be looking at the expanded octet. I would be looking at those other geometries. So we only look at the central atom to determine the geometry. So because we just have 4 bonds, we'd say this is tetrahedral. How else would we use a Lewis structure? So you're going to be using Lewis structures to determine polarity of the molecule. So looking at this, the carbon to chlorine bond is a polar bond. So what that means is the electrons are pulled slightly towards the chlorine atom, but it's tetrahedral. So basically, we have the same atom at all 4 locations. I don't think I have a tetrahedral molecule here. Otherwise, I'd show you one. I thought I had one ready, but apparently, oh, I do. Give me a second. So in this tetrahedral molecule, right, even though this bond is polar, so is this one, and that one, and that one. So essentially, all of the dipoles cancel out, making this a non-polar molecule overall. So that's why we care about Lewis structures. All right, so quick example of a Lewis structure. Let me hop back in the chat, see what else you guys need with. Let's see. Yeah, how do you know ionization energies? Is that something you have to memorize? No, and I am anti-memorization. You know, I love biology as a subject, but you know what I don't love? Is memorizing things. So I was drawn to chemistry because I liked that I could work my way through almost anything, right? Like there are a couple exceptions. What do you need to memorize in a chemistry class? Knowing the polyatomic ions is really useful. There are a couple equations like the one I mentioned earlier, like remembering that the pH is equal to the negative log of H plus. Therefore, the H plus concentration is equal to 10 to the negative pH. A couple things like that will save you time that are useful to memorize, but you don't have to memorize anything associated with trends. All right, so how do you know ionization energies? First of all, like what is the ionization energy? right? So this is the amount of energy needed to remove an electron. It's technically from a gaseous ion. All right, so let's say I'm going to draw a terrible drawing here. All right, this is my nucleus. And we'll make it a nice Bohr diagram. Also incorrect, but for the purpose of this question, it's going to be easy to see. All right, so let's say I have 2 electrons here, and I want to figure out the energy needed to remove this valence electron. So we call this the first ionization energy. As you move in towards the nucleus, you increase the successive ionization energies, right? What we have to think about is what's known as the effective nuclear charge and Coulombic attraction. So if you think about this is a positively charged nucleus. So let's say we had 3 protons and, I don't know, 2 neutrons in this atom. We have 3 positively charged protons in the nucleus. The electrons are going to be attracted towards that because opposites attract. Electrons are negatively charged. The more positively charged protons you have in the nucleus, and the closer those electrons are to the nucleus, the harder it's going to be to remove them. So basically what you need to know with ionization energy is you need to remember atomic radius. Do you have to have it memorized? No. All right, so francium has the largest atomic radius. So atomic radius increases as I move down a group or a family or a column. So many different ways to refer to everything in chemistry, right? So as I move down a column, I'm adding orbitals or energy levels. As I do that, the size of the cloud expands. Okay, therefore the atomic radius or the relative size of the atom from the nucleus to the outermost edge of the cloud is also going to increase. The confusing part is though, as I move from left to right, the size of the radius actually decreases. So francium is going to have the largest atomic energy because as I move across a period or a row and I'm adding more positively charged protons to that nucleus, the electrons are attracted to that positive charge. So the atomic radius actually shrinks slightly as I move from left to right. All right, how is this related to ionization energy, right? Ionization energy is the amount of energy needed to remove an electron. The larger the radius is, the further those electrons are from the positively charged nucleus, and therefore the easier they are to remove. So if you can just remember how the atomic radius changes, you can figure out ionization energy, right? What's going to have the highest ionization energy? The element in that top right corner that has the smallest radius. Why? Because the electrons are closest to that positively charged nucleus, and the Coulombic attraction between those, it's going to be hardest to break that attraction to remove an electron. All right, let me hop back in the chat. Thank you all for being here tonight. I hope this is helpful. Keep sharing this feed. We just want to help as many students as possible. Yeah, all right, so balancing chemical equations, how do you do? Okay, awesome. All right, I'm going to hop back. All right, so let's do percent ionization. And while we do that, how about we'll balance an equation too? So as I'm going through all of these, I will definitely balance. And then it looks like we had quite a few requests for intermolecular forces as well. So let me help with that. All right, so while I'm writing out a problem, there's a question, how did I get so good at chemistry? Like, how do you get good at anything? You keep asking questions. I've been doing this for a long time. So I went to school. I wanted to go into medicine. And, the chemistry department convinced me to join chemistry instead of biology because they're like, well, we have scholarships. So I was like, all right, I'll be a chemistry major. That's fine. And I fell in love with research like my freshman year. I started working in a research lab. I loved it. And I continued on. I went straight to grad school where I was doing astrochemistry. And then I found out, what did I enjoy? I didn't enjoy being in a basement working on my chamber. I enjoyed being a TA. I enjoyed being in the classroom, learning from my students and teaching them. So I think, honestly, I have gotten so much better at chemistry as I have taught. So my recommendation to you is if you're struggling in class, let's say you're taking Gen Chem 2 or you are a chem major, find someone who is just starting out in chemistry and start teaching them, start helping them out, or find a good study group. The more that you try to figure out enough to be able to teach, the better you are going to be at the subject. All right, just a little aside. All right, so let's do a problem with percent ionization. All right, so formic acid, this is kind of a fun compound. So this is a compound, if you've ever gotten bitten by an ant, this is the compound that they excrete that creates that stinging sensation. So even though it's a weak acid, right, by chemistry perspective, right, it'll still burn your skin. So let's say we want to determine the pH and the percent ionization. I'm just going to abbreviate here. A 2.5 molar solution. All right. Okay. I guess we should technically say at standard conditions, if the pKa is, let's see, what is that? 3.75. All right, and I promise if you're here to learn balancing, I will do some balancing too before the session is over. All right, so let's go through this. Okay, so looking at this, we know it's a weak acid because it's not one of the 7 strong acids that you have to memorize. We want to determine both the pH and the percent ionization of a 0.250 molar solution if the pKa is 3.75. So first thing you want to do is you want to start with that equation. This is true for any topic in chemistry, whether you're looking at stoichiometry or you're doing gases or acid-base chemistry. Start with the equation and make sure it's balanced. All right, so let's write out that dissociation equation. So we have CH2O2. If that dissociates, this is acting as an acid, so you're just going to subtract a hydrogen from that to figure out what's left. All right, so dissociation is always going to happen in water. A lot of students forget that. They're like, how do I write an equation? Where do I start? This is where you start, all right? So this is my acid. So therefore, it's going to lose an H, which has a charge of +1. So this becomes CHO2 minus 1. And then what does this become? H3O with a charge of +1. All right, so we're looking at this now and we're like, okay, great. Now what, right? Now what do I do? Yeah, and someone actually just said, okay, do an ice table, and we are about to do an ice table. Let's go ahead and do an ice table here. All right, so what do we need to do? We want to go ahead and figure out, you know what? Actually, we might not even need an ice table with this. So we'll do an ice table next. All right, so we know that we are given our pKa, so we can find our Ka. So our pKa, again, is the negative log of that Ka value. We can rearrange this. That means that Ka is going to be equal to 10 raised to the negative pKa. What is that going to be? Give me a second. 3.75. All right, so my Ka value is 1.778 times 10 to the negative 4. So what is that Ka expression equal to? Again, it's going to be the concentration of your products over your reactants. So this is CHO2 minus times H3O plus over CH2O2. All right, and then what do we know from this? So if I was to write out an ice table, let's see. All right, so my initial change and equilibrium, I like calling them rice tables because I do think it's valuable to have that reaction there as you're doing this, right? We're not going to worry about our liquid. All right, so what am I looking at? So I know my initial concentration was 0.250 molar. I don't have any of this. It is just a 1-to-1 ratio. I should have looked at this. This is balanced. We've just transferred this hydrogen over to that, so it's really easy to balance. So I'm going to subtract x from this. I will add x to each of these, and then I end up with 0.250 minus x equals x and x. So with this, we are going to assume that x is so small compared to that percent ionization that it's less than 5%. So we can just negate that. So this ends up being x times x, so x squared over that 0.250. So now all we have to do is just solve for x. So in this case, X is going to be equal to 0.0067. This is molar because we're looking at the concentration. So that is my H plus concentration. So then therefore the pH is a negative log of H plus, which is that value here. By acid-base, end of acid-base chemistry at least, you will always be able to find that log button on your calculator. All right, so this is 2.176. Again, with sig figs with this, that first number does not count. We have 3 here, 3 there. All right, this is going to have 3 sig figs, so we're just going to keep it as this. So that's the first part of this problem. But we also got a question in the chat. Go over percent ionization. So let's talk about that, because percent ionization, thankfully, is not as tricky as you might think it would be. I feel like the hardest part is like remembering what to put over everything else. So with percent ionization, the whole goal of this is to figure out how much of that weak acid or weak base has dissociated. Because again, by definition, strong acid is something that completely dissociates, weak acid does not. All right, so what I'm looking at in this case is I'm just going to look at my H3O plus concentration over my initial acid. All right, it's a percentage, so we're just going to do that times 100%. Looking at this, I'm going to expect this probably to be a pretty low value, but let's find out. All right, so H3O plus, that's my H plus concentration. We found out that was 0.0067 molar. Okay, divided by my initial concentration, which was 0.250 times 100%. So with this percent ionization, you're not going to have units because you're essentially going to say, okay, how much of my acid has dissociated compared to that initial concentration? And right away, looking at it, you can see not much has compared to that initial concentration of 0.25. So this would be only 2.68% ionized. All right, there are other types of percent ionization problems where you're going to be working in different directions, but that's the gist of it. So hopefully that was helpful. So we just covered ice tables. We looked at percent ionization. We looked at an equation. Let's go ahead and keep going. It looks like we had a question about naming organic compounds. So organic chemistry is tomorrow night. If you're doing some organic nomenclature in Gen Chem, typically you're just looking at like naming the chains and the locations of the different groups, things like that. Make sure to know all of those prefixes and just practice with it. The more you practice, the easier that's going to get. I'd be happy to go through some other naming, or maybe if you need acid nomenclature, we can do that. But if not, come back tomorrow because tomorrow is just devoted to orgo. All right, solubility rules. So I got another question. So can you go over solubility? So with solubility, I think the easiest thing to do is to remember what is always soluble. So what is always soluble? Group 1, acetates, so C2H3O2, nitrates, and ammonium. So for the most part, if you can just remember those 4 things, you can typically cross out whatever that aqueous solution is going to be and easily identify the precipitate. There is a more specific mnemonic too, and that is NAG, SAG, PMS, Castro, Bear. And I know Chegg has some great videos about this mnemonic specifically. So this is what is always soluble. Nitrates, acetates, group 1, sulfates, ammonium, and group 17. And then these are the exceptions. So I didn't include group 17 because there are some exceptions. So with that, then we have PMS, Castro, Bear. So I am not remembering this mnemonic off the top of my head. So check out Chegg's feed so that you have it. And if you can help me, please just put it in the chat because I cannot remember it in this moment. Yeah. Oh, I'm so excited to hear that, Olivia on TikTok. Yeah, all right. So let me hop back in the chat and see. So just a little bit about solubility. All right, there's a question on TikTok. How does electronegativity affect the type of chemical bond form between two atoms. So electronegativity, that's one of the trends that I would say is the hardest to define out of any of those periodic trends. So electronegativity. So I like to tell everyone it's like, imagine there's just this like really contested tug of war on the electrons in a covalent bond. And the more electronegative atom is going to be the one that has the advantage. So basically, the electrons are not going to be shared equally in a polar bond. So the more electronegative atom will have a slightly more negative charge as the electrons shift slightly towards that. So why do we care about electronegativity? How is that going to affect the type of chemical bond? If there is a significant difference in electronegativity, that will determine whether there is a polar or nonpolar covalent bond. So if there is a big difference, so greater than 0.4 in the electronegativity values, then we will see what is known as a polar bond. Okay, that's going to affect all of the intermolecular forces and all kinds of other things. Versus if the electrons are shared equally and we have similar electronegativity values, then we're going to just have a pure covalent bond or a nonpolar covalent bond where the electrons are just shared equally. And that means that you're not going to have what's known as a dipole moment. You're not going to have some of those other intermolecular forces. And that reminds me, I'm supposed to talk about IMF tonight. So let's do another question just with IMF. And I think the easiest way to do this is to look at a structure and identify the types of intermolecular forces that it's going to experience. All right, so let's do some adrenaline. When I start seeing all these questions in the chat, it gets me excited, it gets my heart racing, right? I'm feeling that adrenaline. So let me go ahead and draw this. It's one of these things that I feel like I should have the structure memorized, but I'm not there yet. That's okay. All right. So adrenaline, it has the chemical structure C10, H15NO3. Let me double check. Do I have 3? Yeah. Okay. So this is the structure of adrenaline. So let's look at adrenaline in terms of the intermolecular forces that it's going to experience. So big thing to know, the distinction between intermolecular forces versus intramolecular forces. So previously we were looking at intramolecular forces, which is going to be the interactions within a compound. So if I'm looking at covalent bonds, whether they are pure covalent or polar covalent bonds, those are intramolecular forces. Intermolecular forces are going to be the interactions in between different molecules. All right, so what we need to do though is we need to look at the actual intramolecular forces, the bonds in that molecule, to be able to determine what type of intermolecular forces it's going to experience. All right, so first thing you need to know is, does it have any polar bonds? All right, so polar bonds. So you want to look for polar bonds. And how do we figure that out again? We're looking for difference in electronegativity. Of greater than about 0.4. Some people will say 0.5. It just kind of depends. There's always things like that in chemistry, right? That's what makes it so tricky. There's so many exceptions and like wishy-washy answers like that. All right, so we're looking for polar bonds, which are going to have differences in electronegativity of greater than 0.4. So I will tell you that the hydrogen to oxygen bond is going to be a polar bond. The nitrogen to hydrogen bond is also polar. Carbon to hydrogen is not. That is a nonpolar bond because there is not a significant difference in electronegativity. That would be something that like you should get tattooed on your arm so you never make that mistake, especially not in orgo. The carbon to hydrogen bond is nonpolar. Remember that. All right. So looking at this, I know I have polar bonds. Therefore, this is going to experience dipole-dipole interactions. So dipole-dipole interactions are just interactions between polar molecules. So what do I mean by that? So for example, the OH bond Oxygen is a lot more electronegative compared to hydrogen. So I use the organic shorthand here, but basically this is what this looks like. So what that means is the electrons are going to be pulled towards that oxygen, leaving hydrogen with a partial positive charge. Opposites attract. So if I have another molecule of adrenaline come in, guess what? The negatively charged oxygen is going to be attracted to that hydrogen atom. And it just goes on from there. So that's what's known as a dipole-dipole interaction. We can have a specific dipole-dipole interaction known as a hydrogen bond, and this will experience hydrogen bonding. So name is deceiving with this intermolecular force. Hydrogen bonding, we're not forming a bond. Again, it's an intermolecular force, so it's a force in between different molecules. So with this, you have to have hydrogen in a polar bond and then a very electronegative atom. That can be either oxygen, nitrogen, or fluorine. So in this case, we have several locations for hydrogen bonding to occur. This is one of them. So it is just that interaction between hydrogen in a polar bond and a very electronegative atom. So anything where you have carbon to hydrogen, though, that would not experience hydrogen bonding because hydrogen is not in a polar bond. So be careful with that. All right, so last thing we want to check for is London dispersion forces. And maybe you've noticed I have not discussed one of those IMFs. Put it in the chat if you know where it is, but I'll talk about that briefly. All right, so London dispersion forces experienced by everything. Okay, why? Because London dispersion forces these are just based on the random movement of electrons. So electrons are randomly moving. We don't really know where, we can't really pinpoint where they're at, right? But we know that they are constantly moving in a very random way. So that means that, they could randomly end up congregating somewhere. When that happens, you're going to have a partial negative on one side of the molecule, leaving a partial positive wherever those electrons are not. So that's what a London dispersion force is. It's just based on the random movement of electrons. The larger the electron cloud, the larger the molecule, the stronger that interaction is going to be, because we say the greater the polarizability of that electron cloud. All right, so those are the forces, the IMFs, that this compound would experience. The only one I did not talk about are ion dipole interactions. So with an ion dipole interaction, you have to have an ionic substance that is dissolved in a polar substance. So a lot of things with salt, right? If you dissolve sodium chloride in water, that would create ion dipole interactions. That's actually going to be the strongest intermolecular force. But with these covalent molecules, we're not going to experience that. All right, let me hop back in the chat. I apologize. I've been just talking through all of this random stuff. Let's see, what we only have a little bit of time, but what I will do is if you have left something in the chat and I have not had a chance to get to it, I save everything from these sessions. So I'll save everything and we'll plan on starting with that next week. It looks like, okay, yeah, we'll switch gears and we'll just go through the molar mass of CO2. That's a good thing to end on. The cool thing about these sessions is you just ask your questions and I will answer any and everything. And then Chegg posts all of these feeds right away on their channel, so you have access to them. And I'll hop back in and put in timestamps. So whatever question, if you were looking for something that we missed, for example, we started with titration calculations, you want to go back to that, jump back in, watch that replay, and you have access to all of that. Chegg has so many amazing resources for you. If you have not followed them yet, please follow them on all of their channels. Their TikTok is hilarious. Their YouTube has so many options. It looks like someone on TikTok just says, oh, okay, so we have something about SN2 reactions. Know that Professor Dave is live on TikTok tomorrow night, going through all of the all of that organic. So please make sure to come back for those sessions. All right, so yeah, okay. So what's the molar mass of CO2? And I just posted a tutorial on molar mass. So this is one of the fundamental skills in chemistry. So what you need to know is the molar mass is just the mass of a compound. So it's the number of grams needed to get to 1 mole. So how do we solve this? We find each of these elements on the periodic table. And at the bottom, you'll have the average atomic mass. These are the masses that we're going to use. So CO2 is a molecule that looks like this. So we have 2 atoms of oxygen and 1 atom of carbon. So if I want to find the molar mass of that total compound, I'm just adding up all of those parts. So I have 1 atom of carbon plus 2 atoms of oxygen to get my molar mass, which is at 44.01. Our units are grams per mole because it's the number of grams to get to 1 mole. So thank you all for being here tonight. I hope this was helpful. I really love seeing all of your questions in the chat. It looks like I have a few more questions that just came in. Please come back. We are here weekly at the same time, same place. I will be back next Monday, but there's also a Gen Chem session on Thursday and a Stoic session on Wednesday.